Welcome to everyone. Today's topic is design of tension members. Overlook of tension members. Tension members are linear members in which axial force acts so as to elongate the member. A rope is an example of tension member. Tension member carries loads most efficiently since the entire cross section is subjected to uniform stresses. Unlike compression members, they do not fail by buckling. Ties of trusses, suspenders of cables, stay and suspension bridges, suspenders of building systems hangs from the central core. Buildings are used in earthquake prone zones as a way of minimizing inertial force as a structure, and sag rope of roof purling or other example of tension members as shown below. These are the cross section of tension members. Tension member can have a variety of cross section. As single angle and double angle sections are used in light roof truss as an industrial building. The tension member in bridge truss are made of channels or I sections acting individually or build-ups. The circular rod are used in bracing design to resist load in tension only. This buckles at very low compression and are not considered effectively. Steel rope, wire rope are used as a suspenders in the cable suspension bridges and as mainstay in cable stay bridges. Behavior of tension members. Since axially loaded tension members are subjected to uniform tension stresses, the load behavior is similar to corresponding basic material stress strain behavior. Mild steel member IS 2062 inhibits as inelastic range A minus B ended at the yielding B. This is followed by yielding plateau B minus C. In the plateau, the load remains constantly as the elongated increase to remain 10 times the yield strength. Under further stretching, the materials shows a similar small increase in tension with elongation C minus D compared to elastic range. This range is referred to as a strain hardening range. After reaching the ultimate load D, the load decreases as elongation increases D minus E until rupture E. High strength steel member do not exhibit a well defined yield point and a yield plateau as shown in the figure 3. The 0.2% offset load T as shown in the figure 3 is used taken as a yield point in such cases. Design strength of a tension member, where although steel tension member can sustain load up to the ultimate load without failure, the elongation of the member at this load would be nearly 10 to 15% of the original length, and the structure supports by the member would become unserviceable. Hence, in the design of tension member, the yield load is usually taken as a limited load. The corresponding design strength in the member under axial tension is given by T dg is equal to Fy into Ag divided by gamma m naught, where it is taken from the IS 800. Gamma m naught is a partial factor of safety taken as 1.1 on the plate under tension. This is frequently taken as a bolt hole. The tension stress in a plate at a cross section of bolt hole is not uniformly distributed in elastic range, but inhibits stress concentration adjacent to hole as shown in the figure. The ratio of the maximum elastic stress adjacent to the hole of the average stress on the net cross section is referred to as a stress concentration factor. This factor is in the range 2 to 3 depending upon the ratio of diameter of the hole to the width of the plate, normally to the direction of the stresses as shown in the figure. In static loading, tension member with the hole, the point adjacent to the hole reaches to yield stress Fy first. On the further loading, the stress at the point remains constantly at the yield strength and the section plastifies progressively away from the hole as shown in the figure 4b until the entire neck section at the hole reaches the yield stress Fy as shown in the figure 4.4c. Finally, the rupture tension failure of the member occur when the entire net cross section reaches the ultimate stress Fu as shown in the figure 4d. Since only a small length of the member adjacent to the smallest cross section of the hole would stretch a lot at the ultimate stress, and the overall member along which need not be larger as long as the stress in the cross section is below the yield stress. Hence, the design strength as governed by net cross section at the hole TDN as given 0.9 FUN by gamma m naught, where Fu denotes the ultimate strength of the material, An denotes the net area of the cross section after deduction from the hole, and gamma m1 is a partial safety factor guides ultimate loads. This is the example problem which denotes the tension plate. This type of problem is mainly used for coefficient of to find the efficiency of the plate, where here to determine the tension strength, the tension strength is the given plate is plate size is of 200 into 10 mm with the respective holes as shown in the below figure. The ultimate strength of the steel used are 250 MPa and 420 MPa and 20 mm diameter bolt are used. Here given data or yield strength is 250 and ultimate strength is 420 MPa. We need to calculate the net area first, where here in the given plate we need to divide the cross section of the bolt in 1 1 1 and 1 2 2 1 and 1 3 1 3 1. These three cross sections are calculated below, where AN section 1 1 can be calculated. 200 denotes the width of the plate minus 3 number of bolts into the diameter into the thickness extent, giving the value 1355 mm square. And same for section 1221 as second row and second column, and also AN 1 2 3 2 1 denotes the third column, where TD is should be lesser by comparing the statement 1 and statement 2. Statement 1 formula Ag into Fy divided by partial safety factor. This value at find above, I need to substitute the value, and again for statement 2 0.9 AN Fu divided by gamma m1, I need to substitute the value. Factor of safety is same for both, and factor of safety for gamma m0 is 1.1 and the factor of safety for gamma m1 is 1.25 as IS 800. From these two values we need to take a lesser value as tension, and the final value is 409.75 kN. Efficiency of the plate are calculated using this formula TD by Ag into Fy by gamma m0, where the final efficiency is 0.9. Thank you for watching this video.